Hello, welcome to Basics of Finite Element Analysis Part 2. Today is the 5th day of this particular week, which is the 5th week, and what we are going to discuss today is the method of developing interpolation functions for a linear triangular element. So, that is what we will do. Linear triangle. So, a linear triangle we had discussed, it will have 3 nodes. Node 1, 2 and 3. The coordinates are x1, y1, x2, y2. So, the locations of these nodes are known, because that is from actual geometry, x3, y3. And what we are interested in is figuring out how does UE, which is a function of x and y, it varies over this element. And if it is a linear element and a triangular element, then it will have 3 unknown constants. So, UE will equal C1 plus C2x plus C3 y. Now, earlier in our FEA formulation, we had said that we had expressed UE xy as summation of uj times psi j, right, and j is equal to 1 to n. In this case, n is, what is the value of n in this case for a linear triangle? 3, right. For a linear triangle, n is 3, n is the number of nodes. So, this is how u varies over the area of the element, but alternatively we had also expressed u in this form. So, an alternate expression for the same equation is uj psi j x and y, and j is equal to 1 to 3. I will still write it as n, and n is equal to 3 for first order triangle. Okay. So, what our aim is to find psi j. These are the functions we have to find. I can write UE as C1 plus C2x plus C3y. I can alternatively write it as uj times psi j, sum of that, and so on and so forth. Okay. But our aim is to find C1 psi j's and also C1, C2, C3. Okay. Now, what is the value? So, for node 1, u of x1, y1. At node 1, what will be the value of u? It will be u at x1, y1, because the coordinates are, and that equals, if so I will call this relation 1, I will call this relation 2. If I use relation 2, what will be the value of u at node 1? What will be the value of psi j at node 1? Psi 1 at node 1? 1. Psi 2 at node 1? 0. Psi 3 at node 1? 0. So, the value of u at node 1 will be u1, u1, and if I use equation 1, then what will be the value of u at node 1? C1 plus C2 x1 plus C3 y1. Similarly, for node 2, u equal x2 y2. So, once again for node 2 the coordinates of node 2 are x2 y2. If I use equation 2, what is the value of u at node 2? u2, because the value of psi 1 is 0 at node 2, psi 2 is 1 and psi 3 is 0. So, I get only u2, and if I use equation 1 then I get relation c1 plus c2 x2 plus c3 y2. And finally, for node 3, u at third node equals u3, excuse me, this equals u3 using equation 2, and if I use equation 1 I get c1 plus c2 x3 plus c3, or I can express these three equations in matrix form: u1, u2, u3 equals 1 x1 y1 1 x2 y2 1 x3 y3 c1 c2 c3. So, let us call this equation 3, or I can also in brief I can write it as UE. So, this is for the eth element is equal to some matrix A for eth element. So, this 3 by 3 matrix I call it matrix A times a C vector for eth element. Now, matrix A for eth element is it known or unknown? It is known, because it is a triangle, we have discretized the domain and we have broken it up into a lot of triangles. So, for each triangle I know the coordinates of all the 3 nodes. So, we know a matrix A. What we are interested in knowing is the values of C, because C's are unknown. So, we said that we are interested in finding the values of C's, and we also want to figure out the expression for psi j. So, first we will worry about finding C's, from C's then we will develop expression for psi j. Okay. So, we want to develop an expression for C's in terms of u and a. That is the first step. When you look at equations 3 or 4, the solution for C's will exist if all these 3 equations in equation 3 is having 3 equations, right. If these 3 equations are mutually independent. If one, so what that means is that the rows, the first row, the second row, the third row, they should be different, they should not be linear combinations of each other. If they are linear combinations, when you go to your matrix knowledge, if they are linear combinations of each other, then you cannot invert this A matrix. Similarly, the columns, the first column, the second column, the third column, they should also not be linear combinations of each other. If you can, if they are linear combination, then you cannot invert it correctly. So, matrix A only can be inverted if it is non singular, that is all 3 rows in equation C are mutually independent, that is not linear combinations of each other, and all columns are also mutually independent. So, rows should be mutually independent and columns should be also mutually independent. What does that mean? Example: suppose matrix A is 1 1 1 2 3 7 equation 3. So, this is one example. This is one example. 1 2 3 1 3 4 1 7 8. Okay. Are these linearly independent equations? See here, column 3 equals, so this is a singular matrix 1 plus column 2. If it is a singular matrix, when I try to invert it, its determinant will be 0. So, I will not get a good valid solution, or I will not get a solution. Another example: 1 1 1 2 3 5 7 5 7. Here two rows are mutually dependent, they are not. So, this is again a singular matrix. So, we should not have this condition. If we have this condition, then we will have problem inverting the matrix. So, this concludes our discussion for today. We will continue this discussion in the next class, and we will then cover and actually develop the interpolation functions for this system. So, thanks and look forward to seeing you tomorrow.